So here's a problem. It reads, an ideal gas mixture has a molar analysis of 50% nitrogen, 50% carbon dioxide. What do they give us by that molar analysis? Do they give us the mass fractions or the mole fractions? The Y's, yeah, the Y's and not MFs. Okay. It is cooled at constant pressure from a temperature of 500 to a temperature of 300. How could they accomplish a constant cooling process in your mind visually? What comes to mind? I'm cooling something, an ideal gas mixture, and during that cooling process, it's constant pressure. How could we theoretically achieve that? Yeah. So we basically put a piston of known weight, and that weight doesn't change in a cylinder, so the piston dictates the pressure underneath in the trapped gas, and so the ideal gas mixture is what's trapped, and we then can subject that to some cooling, some heat transfer. And so that's how you would visually, I mean, we have a lot of piston cylinder diagrams in thermodynamics textbooks, so there you go, constant pressure. So it starts at a temperature of 500 Kelvin. It ends at a temperature of 300 Kelvin. Does it tell us the pressure? It doesn't tell us the pressure. But the pressure 1 is equal to pressure 2 is equal to a constant during that process. Does it tell us the amount of mass that's trapped? Like 5 kilograms of this ideal gas mixture. Does it tell us anything like that? So we don't know that either, but the mass is constant because it's trapped. Okay. What do they ask us to calculate? The heat transfer, and they say in units of kilojoules per kilogram of the mixture. So what symbol do we want to say? Oh, I'm asked to calculate this entity, and so I'll have maybe a symbol with subscripts. What symbol would I use for the answer for part A? I would put something like a lowercase q instead of a cap q. A cap q usually indicates total amount of heat transfer in kilojoules. Lowercase q is q per unit mass, which is cap q divided by m. Okay? And what do you think about any subscripts on that? Well, we introduced a subscript 1 and a subscript 2 for initial state 1 and final state 2. So maybe Q1 to 2. Does that look like a good symbol to calculate? So it's the amount of heat transfer per unit mass, 1 to 2. Now we struggle with, should we say that this is into the system or out of the system, or should we just stay with the thermodynamic sign convention? I think if you stay with the thermodynamic sign convention, Q is positive in, isn't it? It's going to go from 500 Kelvin to 300 Kelvin. So if I stay with the sign convention, what answer do I expect? A negative answer. So as long as we're willing to deal with the negative answer, that's fine. Otherwise, switch it and say, I'm going to override the sign convention, turn the diagram around, turn the arrow around for Q, show it that it's coming out, and then calculate a positive heat transfer out of the system. Let's leave it as a positive Q into the system. Let's stay with the sign convention, and we know we're going to calculate a negative answer. Okay? Let's take a look before we jump into part A and finish it. Let's look at part B. What about part B, work? What symbol would you like to use? Lowercase w with subscript 1 to 2. And this subscript 1 to 2, we're going to stay with our traditional direction for the work, where the system is this ideal gas that's trapped. That's our closed system. True? And so that work 1 to 2, first clicker question, is the work 1 to 2, do you expect it to be positive or negative? So if you expect it to be positive, answer A. If you expect it to be negative, answer B. We're going to stay with our traditional thermodynamic sign convention for this problem. So is the work 1 to 2 going to be, do you anticipate it to be positive or do you anticipate it to be negative? Is everybody in? Let's go ahead and stop it and take a look. And how's the distribution of answers? Well, it's not unanimous. What is our positive direction for the work transfer? Work is positive out of the system. Okay, I have an ideal guess. Is it going to expand or contract? It's going to occupy a smaller volume after it's done. It's going to be cooled at constant pressure. So it's not going to lift that piston. It's not going to do work on the surroundings. It's going to receive work. So instead of a positive work of lifting, it'll be a negative work. So the correct answer is B. All that makes sense? So it's funny, but I'm going to look for two answers, Q and W, and both are going to be negative. And they both have the same units of kilojoules per kilogram. What is that per kilogram? It's of the mixture. Okay? Okay. Let's do this. Because I know I can write the first law of thermodynamics. Let's go ahead and write that first law of thermodynamics. Let you write that first law of thermodynamics. Can you write it from memory? Go ahead and write it on your notes. Write the first law of thermodynamics for this problem that you want to apply. But you got to be able to write this down. You can write it down, just kind of say, okay, the total change in internal energy plus the change in kinetic energy plus the change in potential energy is equal to the amount of heat transferred in during the process minus work out. Some people wrote that. True? But you got to bring it to this application. So what do we know about for this problem? And we don't know the mass, so this would be lowercase m times U2 minus U1. Don't leave it as delta U. That you got to say, this is the final state, this is initial state. And I saw one person switching them. Because sometimes it's like, oh, is it delta U? Is that U1 minus U2 or U2 minus U1? This is then MQ 1 to 2 minus MW 1 to 2. And just get rid of the M's. True? So there's our first law. Kind of, I like this form because it's getting close. We don't know the mass, so let's do everything on a per unit mass basis. I'm asked to solve for this, and I'm asked to solve for that. That's my question for part A and question for part B. Do I stand a chance of being able to evaluate U2 minus U1? Starts at 500, ends at 300. Maybe I would say, okay, I'm going to use a model that it's the C sub V times T2 minus T1, true or false? Okay, what do we got for true or false? All right, I'm going to pause and I'm going to say, is this equation right here, is that A, is that true, or B, is that false? I'm going to go ahead and turn it on. Okay, it's starting to collect your responses now. So A, it's true, or B, it's false. Everybody in? Show the results. Can't be both true or false, right? It's got to be one or the other. Okay. Why would somebody call this false? The volume's not constant. You know, I put stuff out there on the internet, and one person, he doesn't know how to teach thermodynamics because he uses C sub V wherever even if it's not a constant volume process. Common misconception, isn't it? Can I use the property specific heat constant volume to describe a change in a property for a substance that's undergoing a process that is not constant volume? Yes, you can. That's one of those things out of chapter 3. So, which answer is correct here? It's a little bit challenging when less than half get it. True? But we have to learn from our mistakes, and then we just press forward. Okay, so this is correct. Okay, a little review for an ideal gas, U is a function of T only. True? True. The definition of C sub V for an ideal gas, for a real gas, for any substance, liquid, solid state, any substance is defined as, that's usually the mathematician's 3 strokes there for an equal sign, is defined as the partial derivative of U with respect to T holding V constant. True or false? True. True. It's true. Okay, so now if U is a function of T only, that partial derivative turns into an ordinary derivative. True? Mathematically? So C sub V for an ideal gas is equal to just the ordinary derivative. If I want to get a change in U, it's just C sub V times change in T for an ideal gas mixture. And that's what we just wrote right here. I need to change in U, C sub V times change in T. True? All right. Now, sometimes somebody says, what happens if this is a function of temperature? Then put the average in here. So I might want to do an average, because I want to not have to integrate C sub V over the temperature range that it's changing. Otherwise, if you want to go U2 minus U1, it's the integral of the temperature-dependent C sub V. You have to get that function times dt. But a lot of times, just pull it out, use the average value, and so it's C sub V average over that temperature range, T2 minus T1. Okay? Makes sense? All right. Little diversion there. Let's get us back on track. Okay. Now, I'm still stuck. Let me see. I know T2 and I know T1. Can I get C sub V for the mixture? And I'm going to say, look, the mixture starts at 300 Kelvin. It ends at 500 Kelvin. I know that some of these specific heats are slightly temperature dependent. What temperature do you think would be a good engineering approximation to evaluate the C sub V at? 400 Kelvin. 400 Kelvin. So could I get the C sub V of this mixture at a temperature of 400 Kelvin? How do I get that? How do I calculate the specific heat constant volume of this binary mixture at 400 Kelvin? So if you're interested in C sub V of the mixture, a lot of times we just leave it off. It'll be the sum of the mass fractions of each component times C sub V of that component. If you wanted C sub V bar, what's that bar mean? Molar specific heat constant volume. It's the sum of not the mass fractions, but the mole fractions times C sub V bar I. So the specific heat of each of those components. Okay? Either on a molar basis or on a mass basis. Both of these equations can be used. So which one do you think is most convenient for this application? It's on a mass basis. So I need to get the mass fractions. So is the mass fraction 50-50? That's the mole fraction, the molar analysis. So this is a molar analysis, true? So I have to do some work. Set up a table to help you organize your work. So the table would be maybe species 1 and 2 What is the first species? Nitrogen. What's the next one? Carbon dioxide. I'm probably going to need the molar mass. Okay. So I look and I find the molar mass of nitrogen 28.01. I should make sure and put the units of kilograms per kilomole for that molar mass. True? Okay. And then I look it up for 44.01. Okay. Which is the heavier molecule? CO2. If I have 1 kilomole of nitrogen, will it weigh less than 1 kilomole of carbon dioxide? Yeah, it will. Okay. So we then put our given mole fractions, 0.5, 0.5. We assume 1 kilomole to start the whole analysis with. If you have 1 kilomole, guess how many kilomoles you have of each of them? I know it's kind of a silly little step there, but I find it helpful to say I'm going to assume I have 1 kilomole of the total mixture. How many kilomoles of nitrogen would I have? 0.5. How many kilomoles of... Then what I do is I say, if I have 0.5 kilomoles of nitrogen, what is the mass? Let me leave it this. What is the mass in kilograms that I have? It's just the product of 0.5 times 28. Yeah, around 14. Okay, so it's 14.005. And I do the same thing. I have 22.005. I add them up, 36.01. So if I start with a mixture of 1 kilomole, it'll have a mass of 36.01 kilogram. Can you tell me the molar mass of the mixture? What's the molar mass, big M of the mixture? 36.01 kilograms per kilomole. We just calculated it. That's how we calculate it, right? So now the next thing is I need to get the mass fractions. How do I get the mass fractions? Is the mass fraction of the nitrogen 14.005 divided by 36.01? And is the mass fraction of CO2 22.005 divided by 36.01? That's the way you calculate it. And so when you calculate, you find the mass fraction to be 38.9% and 61.1%. It's by mass, there's more carbon dioxide because it's a bigger, heavier molecule. Okay. Once I have the mass fractions, I apologize, I didn't leave enough room. Maybe I can grab this and scoot it over some. Try and scoot it over. It's not going to be pretty, is it? Okay. Now I want to calculate. I go and I look up the specific heat constant volume for those entities. Now, luckily, we have a table where they tabulate temperature-dependent specific heats for both nitrogen and carbon dioxide. So I look it up at a temperature of 400 Kelvin. That's our average temperature for the process. It's going to have units of kilojoules per kilogram Kelvin. And we then come across and we read out those C sub V values, 0.747 and 0.750. Not very different, is it? Not very different. You then multiply the mass fraction times the C sub V. You get a number. Then you sum it up and you get 0.749. If you want another digit, 2. 0.74, the specific heat constant volume on a mass basis for mixture. So we just calculated this CC bar average right down here. All right, but I still have one equation. On the left-hand side, everything is known. But on the right-hand side, I have two unknowns. One equation, two unknowns. Can't be solved. So I need something else to help me. Can I go out in my repository of knowledge about thermodynamics and say, I know how to calculate either Q1 to 2 or work 1 to 2? Which one looks a little more appealing to be able to calculate? Q1 to 2 or work 1 to 2? Oh, let's vote. So should I try to find Q1 to 2, another equation to find that, answer A, or work 1 to 2, answer B? Which direction do you recommend that we go? There, it's now on. You see what I'm asking? We used the first law, we got an equation, it's one equation, two unknowns. I've got to figure out how I can calculate one of these unknowns. Ready to stop it? We'll go ahead and stop, and we'll show the results. So a lot of us want to go for the work. Some of us want to go for the heat transfer. Okay, for those, I'll take a brave soul. Those that voted for the heat transfer, what do you think you would do to get it? Second law, it's going to be a little tough, right? Because in the second law, you're going to have that entropy transfer with heat transfer. You do have heat transfer, and the temperature of the boundary, or the temperature of the system's changing as you're transferring the heat. We have it in the second law, integral del Q divided by T of our system, and that T is changing. It's not trivial. So maybe that's helpful to think about it, but it's going to run into a dead end. Why? Somebody else that's a little gutsy and can answer out loud on behalf. You voted for B. Why did you vote for B? What tempted you to vote for B? This is an ideal gas. It's just expanding or contracting. It's in a piston cylinder apparatus. From very first principles, I can get the work. Integral f dx from mechanics. When we moved over here, we modified it with an area over area, and we got force per unit area, pressure. Displacement times area, volume change. The boundary work is the integral P dV. Now I'm going to put it lowercase, specific volume, and this is specific work. Or if you want to write it, cap W is equal to the integral PD cap V. Does that equation look familiar? And this equation you like to use when you have a constant volume, a constant pressure, expansion or contraction. True? So it's a constant pressure process, so this just goes to P times V final minus V initial, true or false? And I can write this as P2 V2 minus P1 V1. So we can at times get the work from first principles because it's the integral f dx, which in thermodynamics, boundary work, PdV, integral PdV. And it's especially helpful when we have a constant pressure process. There you go. Now you say to yourself, looks like a dead end because I don't know P numerically, and they don't give me any information about V numerically. How could you calculate this term? How could you calculate that term? Don't try and do the pressure independent and the volume independent. Say, I think I can calculate the product of P2 and V2. The product of P2 and V2 is equal to R T2. What? Well, way back here we said the ideal gas, there's three things to remember. PV is equal to RT. Is that one thing to remember? And now that I see PV, I can replace by RT. True? So this work, 1 to 2, I can replace by R T2 minus T1. Are we dusting away a few cobwebs? The cobwebs back in Thermo 1 when you're doing a process, but now we're just redoing the process, first law, but now we do an ideal gas mixture. It's just a little harder to go get those properties, a little extra step in between. Okay, so how do I get this R? How do I get this R right there? Is that 8.314? Kilojoules per kilomole Kelvin? Is that what this is, R? All right, another clicker question. Answer that it is A, yes it is, or B, no, it is not. I'm asking, I want to calculate this R right here. And so we know it's this R up here, and this PV is equal to RT. Is that R equal to 8.314? Yes, it is. Answer A. Nope, it isn't. Answer B. Let's show our results. So, very good. So what is the, why is it not 8.314? Because we have two equations, P V bar equal to R bar T. That's a great equation, right? But it's written not on a mass basis, it's written on a kilomole basis. And that R bar is the universal gas constant. This equation right here, PV is equal to RT, is written on a mass basis. How did you jump back and forth between them? Took this and divided by, true? And when you divide by both sides of the equation by cap M, molar mass, you get PV, the specific volume, not per unit kilomole, but it's per unit mass. And you get R. So R, I have to calculate R by R bar divided by the molar mass. I know I erased it, but right there's the molar mass for this problem, 36.01 kilograms per kilomole. All right, so I'm running out of room, but I can calculate this work 1 to 2 from first principles as R times T2 minus T1, and the work comes out to be negative 46.2 kilojoules per kilogram. So in this case, actually, we did calculate part B first, but you didn't have to. All right, once I know that, I can come back up here. I have the C sub V average, and the T1 and T2 are known, and I just calculated the work 1 to 2. I now can calculate Q 1 to 2. When I calculate Q 1 to 2, it's negative 196 kilojoules per kilogram. Okay? Sometimes there's too many routes to correctly solve a problem. This may be one of those where I don't want to add confusion, but I want to explain another route so that you could have calculated Q first and then work later. How could you have calculated Q first? Well, you would have left this as PV minus PV, 2 minus P1 V1. You would have switched that to the other side and combined it with the U's. And then you would have said, oh, look at that. I would have found that Q 1 to 2 is equal to H2 minus H1. Is that dusting off a little shells? You see, oh yeah, I've seen that before. So when I have heat transfer into a closed system, and it's at constant pressure, and it can expand or contract, it's under constant pressure, okay, then the amount of heat transfer is proportional to the change in the enthalpy, which is C sub P times T2 minus T1. I could have done the same thing. I could have put a little column here. I don't have room for it. I could have put a C sub P column, a mass fraction times C sub P column, added them up, and I could have got the specific heat constant pressure for that mixture and used it right here to calculate Q1 to 2 right away. It doesn't look like it would give numerically the same answer, does it? But it will. It will. Okay? Any comments or questions on this problem?
For your R, did you divide by the total molar mass?
Yeah, this 36.01 kilograms per kilomole of our mixture.
You divide by the mass?
Yeah, so if you want to chase the units on this, maybe, is that what you're asking? So 8.314 kilojoules per kilomole Kelvin times, or divided by 36.01 kilograms per kilomole. That's our molar mass. And so the kilomoles cancel, and I'm left with kilojoules per kilogram Kelvin for my constant R. And in this case, R turns out to be, if you want to run numbers later, R is 0.0 0.2309 kilojoules per kilogram Kelvin for this mixture.
So the little m, the units are kilogram per kilomole?
No, not little m. This is molar mass cap m.
Oh, okay. Oh, is it?
Yeah.
Oh, my bad. Yeah.
That's why I stopped right here and I said, I know this is an extra step, but I'm going to say I start with the assumption of 1 total kilomole of my mixture. 1 kilomole of my mixture. Then if I had that many kilomoles of my mixture, I would have 1/2 a kilomole of the nitrogen. How much mass is that? Well, I'd multiply 0.5 times the molar mass. I'd say it's 14.005 kilograms. Do the same thing for the CO2. Add up the mass, and right there, that's how you calculate the molar mass in a nice spreadsheet type of format.
How did you solve for the mass fraction for a specific heat and volume?
This is 38.9%. I know that of this, it's 14 divided by 36.01.
Not that the bar right, where you have the dashed lines through it, kind of.
Oh, I just do the multiply. Multiply the mass fraction times the specific heat constant volume. Put a number here, sum them up.
You summed it? Okay.
Yeah, because the equation, all I'm doing is implementing. I know this is getting bad. I'm implementing this equation right there. See that? C sub V is the sum of the mass fractions times C sub V of each of the components.